Thank you very much. It makes me feel very old when the researchers in the field of DEF weren't born when I started looking at this stuff. Thank you very much. So etronite is a natural material. It can be found in the world naturally. So I won't go too much into what is what is etronite, but I will cover some of the things that I've learnt over the past 30 years. So my first experience with etronite, or delayed etronite, was walking the railway line between Washington DC and Boston. We covered something like 200 kilometres of railway ties, documenting the date they were made and which location in the casting unit they were. At this stage, walking for the 12 weeks documenting ties with 8 other people, we didn't know what we were looking for, but we did notice that a lot of them were really badly cracked. Then we'd come to things like bridges, and they stopped being cracked. We'd get to the other side of the bridge and they'd be cracked again. We'd go under a tunnel, they'd stop being cracked. So what happened during that period is we were actually looking for periods of railway sleepers, railway ties, that had been made with different cements and different aggregates. And so there were lots of papers produced in the early 1990s related to this particular aspect of delayed etronite formation, ASR, combination of delayed etronite formation and ASR. But unfortunately, we will never know the full extent of the information that was available and that was researched at that stage because it got caught up in a legal settlement. And as part of legal settlements, a lot of information gets put in a box and nobody's allowed to talk about it. There are bits and pieces of that information that are in the public. Some I agree with, some I disagree with. But anyhow, this is what started my road down DEF. Okay. So, as we just mentioned, we know about etronite. This is a picture of typical etronite that we'll find in concrete. And it always occurs. It occurs in every piece of concrete we make. So etronite's not an unusual mineral. It also, if you wet the concrete and dry the concrete, the etronite will move. It'll appear in air voids. So we know etronite's mobile, we know it'll form, and we know it's in every bit of concrete. Sorry, I'm trying to work out where. So this is the typical concrete distress that was observed on the railway sleepers. It was very rapid. Within 5 years of the concrete being made, the concrete was cracking severely. And it was enough to make these railway sleepers unusable and have to be replaced. And it was a very large dollar settlement. At that stage, it was something like $200 million being litigated between various parties. There have been examples of delayed etronite formation claimed throughout the world, in France, in Sri Lanka, in Europe, in the United States, in Texas. So the question is, what's going on with this? Why did it suddenly appear? And it's one of the petrographers that I knew many years ago said, we probably didn't know what we were looking for. We didn't have the tools of scanning electron microscope, so we probably attributed some things that were delayed etronite to ASR. So it may have been a difference of how we look at information. So we might have had delayed etronite formation occurring for the last 50 years and didn't know about it. So this was one set of tests that was conducted at the company that I left. I set up the program, then left the company. But it's some tests finished by Sharon Tracy and some of her colleagues, where they took 6 different cements with 6 different characteristics and cured them at different temperatures, ranging up to from 65, 70, 80 and 90 degrees. And what they found is even at 90 degrees, one of those cements didn't show expansion. Now this correlates with the information we just heard that concretes with low alkalis and low sulfate contents may be less susceptible to delayed etronite formation than those that have high etronite contents. There's a piece of research which I think needs to be brought back and looked at, and this was by Kellum, who did a whole bunch of laboratory tests on a very wide range of cements. He looked at 128 different cements. And he found that Curing them at normal temperatures, nothing expanded. Curing them at 70 degrees, nothing expanded. Curing them at 80 degrees, he had 14% of the cements expanding, which meant most of them didn't expand. But once he got to 90 degrees, over 50% of those cements showed expansion. So this was showing that there is a critical curing temperature, but it's also showing that the cement chemistry may be playing a more important role in the expansion than actually the temperature itself. So this is another graph that he produced, and it shows that depending on the alkali content and the sulfate content, the cements may show different expansions. And so this data is very similar to what we just saw on a wide range of cements. And this work was produced a good 20, 25 years ago. So out of all the data that Kellam produced, he came up with an equation where he could relate the cement chemistry to whether it did or didn't expand. And he had a critical value that he came to, and he found that the C3A content, those rapid accelerating cements, which we use commonly in precast, were more susceptible to delayed ettrinite formation. And those with certain sulfate and alkali contents were susceptible to delayed ettrinite formation. So we did have a formula that helped us analyse some of the early cements 20 years ago. There have been other people develop equations. Zhang developed another equation where he looked at sulfate aluminate content ratios and the C3A contents. But overall, the research has shown that sulfates less than 3% don't result in expansion. And I think that's what we're seeing fairly consistently, that the cement chemistry and the sulfate content is a critical factor. So one of the things I did in the 90s was to take the equation that Kellam had developed and apply it to the cement databases. And in the United States, there were two cement databases that Portland Cement Association maintained. One was developed in 1953, and the other one was in 1994. And out of that research, I was able to show that there was an increase in the likelihood of delayed ettrinite formation with the modern cements compared to the older cements. And this was attributed to the grinding, the higher sulfate, the higher alkali, and the increased C3A. Now, all of those four factors are great if you want strong concrete really fast. I'm going to skip over that one. Okay, so the other thing that Kellam managed to do was he put pozzolans into concrete mixtures and with the cements that had previously shown expansion. And what he was able to show, even if we got expansion of different mixtures, by adding the pozzolan, he was able to reduce that and basically eliminate any expansion due to delayed ettrinite formation. So the use of pozzolans, 25% fly ash, 30% fly ash, and all the others. You can see the yellow are fly ash, the right are blast furnace slags. Basically eliminated the risk of delayed ettrinite formation. So there's a difference between concretes using plain cements and concretes using mixtures of cement and pozzolans. So there's been additional work done. This is also work from the UTS, where they looked at mortar expansions. And they were unable to really come up with expansions using the Australian concretes. So again, the studies keep going on. Australian concretes with its low sulfate, low alkali, is more immune to delayed ettrinite formation. Now you may wonder why I'm back talking about delayed ettrinite formation. I thought I'd left that subject 20 years ago. But it turns out to be important when you're actually trying to place mass concrete. Because in mass concrete, what happens is the concrete develops heat. And we're now having to match temperature limits that are being assigned by the specifying agency that may make it very difficult to place the concrete. I remember about 25 years ago, the Portland Cement Association was seriously discussing putting a limit on the temperature of concrete at 60 degrees Celsius. To which I responded, that's fine, it's your product, do whatever you like. But I said, don't expect to sell concrete in Texas or ever sell cement to the precasters, because it's very hard to make concrete in those two atmospheres below 60 degrees Celsius. So what is the right temperature is really the whole thing. When we look at temperatures in mass concrete, we can change it using pozzolans, we can reduce the temperature, but sometimes we just can't get the concrete cool enough to meet very restrictive temperature restrictions. So when I looked at the temperature limits that were worldwide and those that are in Australia, typically Australia has adopted lower restrictions for temperature than they have elsewhere. And the difference typically at 75 degrees is out of AS 5100, 70 degrees appears in some of the government specs. It makes it very difficult to place concrete that's sort of 2 metres thick without exceeding those temperatures. You're looking at having to reduce your concrete temperatures down to something like 26 degrees. How do you get there? You use ice, you might need to use cold water, you might need to cool your aggregates, but again, you may exceed those limits. A number of the different groups also allow increased limits if you have pozzolans in your concrete. And this is the approach that's been taken through ACI and also more recently through the Japanese Standards Institute, where they allow you to go to a higher temperature if you've got pozzolans in your concrete. So all the various limits are in the paper. I won't discuss them here. They're all available. But again, as you know from the research from Kellam, adding pozzolans to concretes basically eliminated the risk of expansion, even when the concrete was heated to 90 degrees Celsius. So I want to conclude with delayed ettrinite formation has been observed in a very limited number of structures, but I'm not going to discount those structures. Those structures that have DEF, it's a significant problem. So people have put limits, and those limits on temperature range anywhere between 60 and 85 degrees. And choosing those low limits may really restrict the use of concrete. It's more linked to the cement chemistry than the temperature itself. You can make cements that are immune to DEF at 90 degrees Celsius. Now, they might not be all that useful as a cement material. They may not get fast, they may not get strong, but you can do it. And the additions of pozzolans, slags, and fleisches basically eliminate the risk of delayed ettrinite formation. And for this, I'm recommending that the agencies in Australia consider changing their specs to allow modification to these temperatures if pozzolans are being used. Thank you.